Hi everyone, my name is Abdullah Keskin and today I will be answering the questions for the last lab of ee361. So let me start with the first one. It was all about the IP scale or IP code. IP scale is referred as an ingress protection code, or sometimes it can be referred as international protective degree. It's all about the resistance of DC machine against some ingress of some materials. For example, it consists of two numbers, IP, XY. The first number shows the resistance of our DC machine or electrical machine against solid materials, and the second number Y represents the resistance of our DC machine against water intake, water ingress. To make our concept more clear, I will refer this website here. If you remember, in our case, the number was 54. The first number was 5. It represents the resistance of our DC machine with respect to dust. 5 means dust, and the second number was 4. Let's see the 4 is the resistance of our DC machine or protection against our DC machine with respect to splashes of water. Okay, this is the test condition. So it's basically all about the resistance of our DC machine with respect to dust and the water. In the second question, it was asked that despite our field current 0, but we have some still induced voltage. This is actually, first it was asked that if we had expected some kind of behavior or we didn't. Actually, we had expected some kind of behavior because if you remember, we are using core materials in our DC machines, and the core materials are ferromagnetic and they have some hysteresis behavior, which means that when we increase our field current, think this one is a field current, when we increase our field current to some value, then we make it to 0. When we make it to 0, even if we make it to 0, we have some fluxes in our stator. And as a result of this is called residual flux or residual magnetism. As a result of this residual flux, we still have some flux in our DC machine. And if you remember the back EMF equation, it's equal to K sub A, which is armature constant, K sub phi field winding constant, and IF V mechanical, omega mechanical. We make this is valid for linear region, I mean this region, but when we make IF 0, we have some fluxes, so it's better to use this equation part. So if we have flux per pole, which is a residual flux, this is just a constant, and we still have V mechanical, it's expected to have some more induced voltage even if we make IF 0. As I mentioned for the last time, to summarize, we have still fluxes, which is a residual flux, and we have some V mechanical. As a result of this, it's expected to have some more induced voltage. And let's go on with the third question. It was all about field current control method. First, let's refer here. In this configuration, we have some constants. Our terminal voltage is constant and our armature current is constant. They kept constant. So, and this experiment conducted with the shunt connection of DC machine. So this is V terminal, this is constant, and this is armature current. This is also kept constant, if you remember from the experiment. And then we can write the back EMF equation, I mean EA. EA can be written as these parameters, Vt minus R sub A. By the way, this is just disregard this one, okay? Times array times IA, sorry. And actually, let me write it again. I times A, which is also constant, Array is just the resistance of the winding, so it's also constant. This constant, these are all constant, means EA should be constant. So let me refer my notes again. If EA is constant, we should look at this equation. KA and KF are already constant, but what we changed is that we are playing with this rheostat. As a result of this rheostat, since VT is also constant, we can play with the IF, our field current. And if we can play with our field current, we should look at this part of our equation. Since Ka and Kf are constant and also EA is constant, increasing IF field current means we need to decrease the omega mechanical because EA is also constant. So this implies that the speed of our motor is inversely proportional with field current. Increasing field current decreases our speed of our motor. This is all about the field current control method, and key point here is the EA should be constant. If it is not constant, we cannot observe such inversely proportional relation in a better way. This would be better. Okay, so let's go on with the last question, and it was all about terminal voltage control method. And we used, for this experiment, we used separate excitation, separately excited DC machine. So let me show it here. And this is the constant part, so which means IF is constant. We are not changing it. But what we play with is V terminal voltage. We increase or decrease this, and we try to observe what happens. Actually, it would be better if IA was kept constant and torque was kept constant, but they are not in their rated value, so they were not constant. But the key point here is that R sub A is just a very small value, so we can disregard it, and we can disregard the drop on this resistance. And also one more thing, IA was also a low value, so the drop on this is very small. So we can write this equation for motoring mode, I mean VT, minus I sub A times RA equals EA, right? And even if we don't disregard this term as a zero, the drop or this term will be very small. So when you decrease VT or increase VT, EA will directly change in the same manner. And what we did was actually this: we decrease VT and we try to observe the EA. So let's go on with my notes again. Okay, one thing important here is that Ka, Kf, they are already constant, and IF also kept constant because this is separately excited DC machine, which means that if any change in EA points out the same change in the omega mechanical speed of our rotor, so this means that EA is directly proportional with omega mechanical. And also remember that EA is also proportional to VT, so we can write here as they are also proportional with our terminal voltage. And this is the last part of our question. Thank you for listening.